Stationarity, ACF, PACF and ARIMA, a beginner's path to time series analysis. Welcome! In this lesson, you will gently learn key foundations of time series analysis in Python. We will start from the basics, explore essential concepts, and practice hands-on with real-world data. If you have never touched ARIMA, autocorrelation, or stationarity before, do not worry, you are in the right place. Running the cell now. Hide unnecessary warning messages to improve user experience. Import the warnings module to control warning messages. Import numpy as NP. We set the random seed to 42 for reproducibility. Import specific warning classes to selectively ignore them. Ignore warnings of the type value warning to reduce clutter. Ignore warnings of the type convergence warning to keep output clean. Ignore warnings of the type runtime warning for a clearer output. Ignore all remaining warnings to avoid distraction. Running the cell now. Here, the code sets up a clean and distraction-free environment by suppressing common warning messages you might see during time series analysis. Notice there's no output. This is intentional to keep your workspace clear as you proceed with exploring stationarity, ACF, PACF, and ARIMA modeling. This step ensures smoother learning without interruptions from non-critical warnings. What are time series and why do they matter? A time series is simply a sequence of measurements ordered by time. Examples: daily temperatures, monthly airline passengers, stock prices. Understanding patterns or predicting the future needs tools designed for sequences. Running the cell now. We are loading the classic airline passengers dataset. It contains monthly totals of international airline passengers over several years. Pandas lets us read CSV files from the web easily. We also import matplotlib. It is the main tool for creating plots in Python. We import numpy for numerical operations, which might be useful later. This URL links directly to a popular and simple time series CSV file hosted on GitHub. We read the CSV file, parsing this month column as dates and setting it as the index for easy time-based analysis. We print the shape of the dataset to see how many rows and columns it contains. We display the first 5 rows to verify the data was loaded correctly and to understand the column structure. Running the cell now. This output shows the loaded airline passengers dataset contains 144 monthly records with one key column, passengers. Notice how the index is time-ordered by month starting in 1949, illustrating the fundamental structure of a time series, measurements arranged sequentially by date. This setup is crucial for exploring trends and seasonality in later lessons. Try printing df.tail, too. What do you notice at the end of the timeline? It is always good to begin with a simple plot. This line chart shows passenger numbers over time. Large dips and peaks may stand out. Labeling the y-axis keeps things clear. Now we display the chart so you can see the trends at a glance. Running the cell now. This plot shows the monthly airline passenger counts over time, allowing you to visually inspect trends and seasonal patterns in the data. Notice the overall upward trend and repeating cycles, which are key features that time series analysis aims to capture. This initial visualization helps set the stage for understanding the structure and behavior of sequential data. What is stationarity? A time series is stationary if its properties, mean, variance, do not change over time. Why care? Stationarity is a key assumption for most forecasting methods, especially ARIMA. Look at the chart above. Does the airline passengers series look stationary to you? Running the cell now. Let us check for stationarity by looking at rolling averages and rolling standard deviations. We pick a window of 12 months, representing 1 year at a time. This gives us the moving average. If it stays flat, the mean does not shift much. The moving standard deviation measures how much values spread out in each window. We open a new figure window to plot. We show the original data curve. Rolling mean is added. You will see if it trends or stays steady. We also plot the rolling standard deviation to see how spread changes. The legend explains which curve is which. We add a title for clarity. Now, we show the figure. Notice if the rolling curves remain steady or not. Running the cell now. The plot shows the original passenger counts alongside their 12-month rolling mean and standard deviation. Notice if the rolling mean and variance lines are roughly flat, indicating stable mean and variability over time, key signs of stationarity. This visual check helps confirm whether the time series meets the stationarity assumption needed for forecasting models like ARIMA. Pause and ask yourself, what clues in the plot might suggest the data is not stationary? To test stationarity more formally, we use the Augmented Dickey-Fuller test, or ADF test. This function checks if the series has a unit root, which would suggest it is not stationary. The test gives us a statistic. The more negative, the stronger the evidence. Here we see the test statistic. The p-value tells us how likely it is to see this result if the series were non-stationary. A value less than 0.05 usually means the series is stationary. Running the cell now. The output shows the results of the Augmented Dickey-Fuller test, which checks if the passenger's time series is stationary. Here, the ADF statistic is close to 0 and the very high p-value, 0.99, means we fail to reject the null hypothesis of non-stationarity. This confirms that the series properties change over time, highlighting why stationarity must be addressed before applying forecasting models like ARIMA. How to make a series stationary, differencing. Many series need to be transformed to become stationary. Differencing means subtracting each value by its previous value. This removes trends and seasonality in many cases. Let us try this and see what changes. Running the cell now. We subtract each month from the one before it. This is called first-order differencing. We drop the first value that became missing after this operation. Now, we create a plot to check the effect. The plot shows the difference series. Is it flatter and steadier? Add a legend just in case. Set a title to label the plot. Now, display this new view. Notice how much smoother it is. Running the cell now. The plot shows the result of first-order differencing, where each point represents the change from the previous month's passenger count. Notice how the clear upward trend in the original data is now mostly removed, making the series more stationary. This confirms that differencing helps stabilize the mean by eliminating trends, which is key for many time series analyses. Let us repeat the Augmented Dickey-Fuller test. Now we apply it to the difference series, not the original. A more negative statistic means stronger support for stationarity. Check if the p-value is now below 0.05. That would show our transformation worked. Running the cell now. The output shows the Augmented Dickey-Fuller, ADF, test results after differencing the series, where the ADF statistic has decreased, indicating reduced trend. Notice the p-value is now around 0.054, close to the common 0.05 significance level. This suggests the series is closer to being stationary but may still need further transformation or testing. This connects to the lesson's intent by demonstrating how differencing can help stabilize the series by reducing non-stationarity. What are ACF and PACF? ACF, autocorrelation function, shows how today's value is related to past values. PACF, partial autocorrelation function, removes indirect effects, showing only direct relationships. We use these to choose ARMA and ARIMA models. Running the cell now. We are going to look at the ACF and PACF plots of our difference series. These plots help pick the best ARIMA model by showing which lags are most important. We set two plots in one row for easy comparison. The ACF plot shows how much current values relate to previous ones. Major spikes point to strong relationship at that number of lags. The PACF plot does a similar thing, but shows only the direct connection at each lag. We adjust space so nothing overlaps or looks crowded. Let us see both together. Notice where the blue bars are higher than the shaded area. Running the cell now. This output displays the ACF and PACF plots for the different airline passengers' data, helping us identify the key lag relationships after removing trends. Notice the significant spikes in the ACF, indicating lingering autocorrelation, and the PACF spikes, pointing to direct lag effects useful for selecting AR and MA terms in modeling. These plots guide us in choosing the order of ARIMA components by revealing which past lags have meaningful influence on the series. Basics of ARIMA models. ARIMA stands for Autoregressive Integrated Moving Average. It combines AR, autoregression, which uses past values. Integrated, that is, differencing as above. MA, a moving average, for error smoothing. The three numbers P, D, Q in ARIMA indicate P, number of autoregressive terms, and you look at PACF for clues. D, difference order, or how many times you difference. Q, moving average terms, and you check the ACF. Let us try a first ARIMA model soon. Running the cell now. Fit an ARIMA model with parameters P equals 1, D equals 1, Q equals 1 to the data and visualize the forecasted values. Import the ARIMA class from the Stats Models library for time series modeling. Import the Warnings module to control warning messages during model fitting. Import specific warning classes from Stats Models to filter them out during fitting. Ignore value warning messages to avoid clutter in the output. Ignore convergence warning messages which may appear during model optimization. Ignore runtime warning messages to keep the output clean. Create a copy of the data frame to avoid modifying the original data. Set the data frame index frequency to MS as month start, so ARIMA can interpret the time index. Begin a try block to catch errors during model fitting and forecasting. Initialize the ARIMA model on the passengers column with order 1, 1, 1. Fit the ARIMA model to the data and save the results. Print the summary of the fitted ARIMA model showing parameters and diagnostics. Generate a forecast for the last 12 months using the fitted ARIMA model. Plot the last 24 months of actual passenger data with circle markers labeled actual. Plot the forecasted values for the last 12 months with cross markers labeled forecast. Set a title on the plot describing that it shows ARIMA forecast compared to actual data. Add a legend to distinguish actual data from forecasted values. Show the plot to visualize the comparison. If any error occurs during fitting or forecasting, print an error message describing it. Running the cell now. This output shows the summary of fitting an ARIMA 111 model to the monthly passengers data, where the coefficients for the autoregressive RL1 and moving average ARMA.L1 terms are statistically significant. Notice the AIC and BIC values, which indicate model fit quality for this difference series, connecting to the lesson's intent, capturing patterns using past values and errors. This confirms that ARIMA can effectively model the time series with integration D equals 1 to handle non-stationarity. Try changing 111 to 212. Does your forecast improve or get worse? Missing data can happen for many reasons, like misreporting or sensor errors. We make a copy of the dataset, then introduce 5 missing points to show what can happen. We assign none to rows 10 to 14 to simulate missing values in the data. Let us print out how many missing values there are now. With time series, it is common to fill missing values by carrying forward the last known observation. Here we apply forward fill and check the first 20 rows to see the result. Running the cell now. Here, the output shows that 5 missing values were introduced and then forward-filled, a scene where the value 119 is repeated across those missing months. This confirms the effectiveness of forward fill in handling gaps by propagating the last known value, which is crucial for preparing clean time series data before fitting an ARIMA model. Let us practice. Here we create a synthetic random walk, which is a classic example of a non-stationary series. NumPy lets us create random numbers easily. We set a seed for consistency, so you see the same result every time. A random walk is made by adding random steps together. Now we plot the random walk. Give the plot a title so the context is clear. Show the chart. Does this look stationary to you, or does it wander without returning? Running the cell now. The output shows a plot of a random walk series, which visually exhibits a non-stationary pattern with trends and large fluctuations over time. This highlights why differencing might be needed in ARIMA modeling to stabilize the series by removing such trends or drifts, aligning with the lesson's intent to identify when integration, the IO in ARIMA, is necessary. We start by indicating that we will check the stationarity of the random walk using the ADF test. We import the addFuller function from the stats models library, which performs the augmented Dickey-Fuller test. We run the addFuller test on the random_walk data to obtain the test results. We print the p-value from the test results to assess stationarity. Running the cell now. This output shows the p-value from the augmented Dickey-Fuller test applied to the random walk data. Since the p-value is quite high, 0.60, it indicates the series is non-stationary, meaning its statistical properties change over time. This confirms why differencing, the integrated part of ARIMA, is necessary before modeling such data. Let us check your understanding. If you see a time series that trends up over time, which transformation should you try first? You are prompted to enter your answer: A, take log, B, difference, C, z-score. If you pick letter B, which stands for differencing, you get encouragement. If you pick another choice, we nudge you to try differencing first instead. Running the cell now. This output confirms the student correctly identified differencing as the key first step to make a drifting time series stationary by removing trends. This reinforces the AR, autoregressive, part of ARIMA, which relies on stable, non-trending data to model relationships with past values effectively. Noticing this ensures the data meets ARIMA assumptions before proceeding. Let us make a synthetic time series with a wavy shape and some noise. We plot it so you can see the movement. The curve should look like waves with some random bumps. Give the chart a clear title. Show the picture. This will be your target for ARIMA. Now we import ARIMA again to fit this synthetic series. Set up the ARIMA model with simple settings: AR equals 1, no differencing, no moving average. Fit the model to all 120 points. Now predict the last 20 points to see how ARIMA handles unseen data. Plot actual values for all points. Add the ARIMA forecast for the last part, dashed for clarity. Show the legend so you can tell real and prediction apart. Title the figure so the context is clear. See both lines together? How close did the forecast get, even on this unpredictable series? Running the cell now. The first plot shows the synthetic time series combining a sinusoidal pattern with noise, helping you visualize the data's cyclical nature. The second plot overlays the AR1 model's forecasts on the last 20 points, letting you observe how well the ARIMA 100 captures the recent trend and smooths out noise. This demonstrates the AR component's ability to use past values for short-term prediction in a noisy, periodic context. Extra tips. 1. Always visualize your data first. 2. Check for missing values before modeling. 3. Try multiple differencing levels if stationarity is uncertain. 4. Use ACF and PACF plots as model guides, not strict rules. 5. Save your notebook often. Ready for more? Try changing ARIMA settings or exploring the sunspots dataset next. Running the cell now. Time for a mini project. Simulate a website with visits increasing each month, plus seasonal ups and downs and a touch of noise. Set a random seed for consistent results. Create a slow, steady upward trend to represent site growth. Add seasonal waves to reflect annual cycles. Add some random noise to imitate real-world unpredictability. Combine them all for the total website visits per month. Plot the finished series to see how it looks. Title the chart for clarity. Display the result. Running the cell now. This plot shows a clear upward trend mixed with a repeating seasonal pattern, representing simulated monthly website visits. Notice the smooth increase over time combined with cyclical fluctuations, plus some random noise. This visualization confirms the intended trend and seasonality in the data. Visualizing like this first helps identify key features and potential challenges before any modeling. Let us check if our simulated web visits are stationary. Open a new figure. Plot the original series in blue. Add the rolling mean to see if average visits shift. Show rolling standard deviation too. Add a legend to tell curves apart. Title the figure to keep it organized. Show your visualization. Now apply the augmented Dickey-Fuller test and print out the result. The p-value reveals if the visits show a trend or are stationary already. Running the cell now. This plot shows the original simulated website visits along with their 12-period rolling mean and standard deviation, helping us visually assess stationarity. Notice the rolling mean and std-dev don't appear stable over time. Correspondingly, the augmented Dickey-Fuller test yields a high p-value, (0.96), indicating we cannot reject the non-stationarity hypothesis, so further differencing or transformation is needed before modeling. This aligns with our lesson tip to visualize and test stationarity before proceeding. Minute project tip: try differencing website_visits and rerunning the ADF test. Recap, key lessons and where to go next. You learned how to plot and inspect a time series, what stationarity means and why it matters, how to use rolling averages and the ADF test, when and why to difference your data, basics of ACF and PACF plots for ARIMA, how to fit ARIMA and check forecasts, how to handle missing time series values, where these skills apply, from web visits to weather. Explore, experiment, and most importantly, have fun learning time series. Running the cell now. Thanks for learning. Share your results and subscribe. Thanks for studying stationarity and ARIMA basics with us. Try the challenge exercises on your own data. If you liked this lesson, subscribe to our channel and share your graphs. See you next time for more hands-on data science. Running the cell now. Practice prompt: run a PACF plot for your favorite time series and share your findings in the comments.